Hello friends, today I will discuss the vector diagram of three-phase induction motor. So the base for the vector diagram of three-phase induction motor is the equivalent circuit of the three-phase induction motor. So for that, the assumption is the motor that is used here is high HP motor, that is 2.5 HP motor and above. So in that case, the equivalent circuit becomes like this. This is the applied voltage to the stator winding represented by V1, and the input current to the stator per phase is called as I1, and this is the no load current represented by I0, and this is the core loss component represented by resistance RC, and the current flowing in this we call as IC, and this is the magnetizing component XM, and the current flowing through this IM flowing is IM, and this is also called magnetizing component, and this current is responsible for flux creation in the three-phase induction motor. The vector sum of IC and IM is nothing but no load current of the three-phase induction motor. That can be shown like this. This is I0 vector is equal to IC bar plus IM bar. Next, this is I2 dash, means it is the secondary current referred to the primary side. So if we assume the turns ratio between the rotor and the stator per phase is unity, then this becomes simply I2, and this is R1, this is the stator winding resistance per phase. X1 is the stator reactance per phase. R2 dash is nothing but the rotor winding resistance referred to the primary side represented by R2 dash, and if the turns ratio between the stator and the rotor is unity, then this can be simply written as R2. Similarly, X2 dash is nothing but the rotor winding reactance referred to the primary side, that is stator side, and if the number of turns ratio between the stator and the rotor is unity, in that case X2 dash can be written as X2, and this is the mechanical equivalent load, that is nothing but 1 by S minus 1 into R2 dash. Here S is the slip that is dictated by the rotor speed, and here applying the KCL at this node, it can be written as I1 is equal to I0 plus I2 dash. From this we can write I2 dash is equal to I1 minus I0. So knowing all this, we can draw the vector diagram for this. So taking here V1 as reference like this, the core loss current component, which is current flowing in the RC, that is resistance, which is always in phase with the applied voltage, that is V1, that is IC and V1 are in phase like this. And next there is a magnetizing current, that is this will flow through the inductor, that is this XM. So the current flowing in an inductor lags the applied voltage by 90 degrees, So it can be shown like this. This IM lags the V1 by 90 degrees. As we know, I0 is nothing but vector sum of IC and IM. So when we draw the vector sum, I0 becomes like this. So let us say I1 is the input current, and let us assume that this I1 is lagging V1 by some angle like this. And I0 is already drawn vector, and now it is necessary to know what is the I2 dash, because I1 is the vector sum of I0 and I2 dash. I0 is already drawn, I1 is also drawn, and to know what is that I2 dash, so draw a parallel line to the I0 vector from the tip of the I1 like this, and the value should be equal to this I0. Then draw a line from here to here that represents I2 dash. That is, here from this equation we can write I2 dash is equal to I1 minus I0. I1 is drawn, I0 is known, so from I1 I0 is subtracted like this. It's drawing opposite. Then the resultant of this and this is nothing but I2 dash. This is the simplest way of drawing the vector diagram for a three-phase induction motor using the approximate equivalent circuit of the three-phase induction motor. So let me summarize once again. To draw the vector diagram, it needs the approximate equivalent circuit of three-phase induction motor like this. Here applied voltage per phase to the stator is V1 and the input current is I1, and this is the no load current components, that is, one is RC, the other is XM. The current flowing through the RC is nothing but IC, and current flowing through the XM is nothing but IM. The vector sum of this IC and IM is nothing but I0, and the current flowing in this branch is nothing but I2 dash, and which we call as the secondary current or the rotor current referred to the primary side. When the rotor to stator winding turns is unity, then this can be written as simply I2, which is also approximately equal to input current. And R1 and X1 are nothing but the stator winding resistance, and the reactance is per phase. And R2 dash is nothing but the rotor resistance per phase referred to the stator side. X2 dash is nothing but the rotor reactance per phase referred to the primary side. And from this we can see that I1 is equal to I0 plus I2 dash, and I2 dash is nothing but I1 minus I0, and I0 is nothing but the IC plus IM. And here is the slip which depends on the rotor speed, and this is the R2 dash, that is 1 by S minus 1. This is also called dynamic resistance or dynamic load connected to the three-phase induction motor. Once all those things are known, so that equivalent circuit parameters can be drawn like this, that is, the voltage vectors, current vectors are shown like this. This is the applied voltage V1, and this is the IC which is in phase with V1, and IM lags the V1 by 90 degrees like this. The resultant of IC and IM is I0, and I1 is drawn with certain angle lagging with respect to the applied voltage like this, and because I1 is nothing but the vector sum of I0 plus I2 dash, so to get the I2 dash position, so we write the equation like this: I2 dash is equal to I1 minus I0. To get that minus I0, so draw a vector at the tip of the I1 backwards and parallel to I0 and equal to I0, and then join the line from here to here, then that becomes I2 dash. So this completes the vector diagram of three-phase induction motor using the equivalent circuit.